This is video 3.4.1, and the goal of this video is to be able to solve exponential equations. So these are equations where the exponent is actually where the variable exists, the x or the y or the z, whatever it may be. So you're going to see three strategies in this video. Be sure to write down the three strategies and at least get one example from all three strategies. The first strategy is to use like bases. So what we're going to do is convert things so they have the same base. We'll see two examples like this. The first example is 2 to the 3x minus 8 equals 16. The left-hand side is already written in exponential form, 2 to the 3x minus 8. The base on the left is 2. So what I'm going to do is use the same base on the right and rewrite 16 as 2 to the 4th because that's equivalent. I have like bases because I have 2's on both sides of my equation. Now, the good news is I simply look at the exponents. These two exponents have to be the same in order for the expressions on either side to be equal. So I simply drop the 2 and solve the equation 3x minus 8 equals 4 because the exponents have to be equal. Now I solve just using my basic equation skills by adding 8 and dividing by 3, and I get an answer of x equals 4. The good news with exponential equations is that you should be able to check your answer by plugging in your solution and seeing if you get equivalent expressions on either side of the equation, as you see here. And it looks like we get 16 when we plug in 4 into the expression 2 to the 3x minus 8. Let's take a look at another example. This one's a little bit less obvious. In this example, notice that we already have two bases that are different, 27 and 9. I want them to have the same base. The same base is not going to be 9 because 9 to the second power is 81, which is not 27. And also 27 is hard to rewrite as base 9. But what we can do is rewrite both of them with the base of 3 because 27 is 3 to the third and 9 is 3 squared. What I'm going to do now is replace the 27 with 3 to the third and replace the 9 with 3 to the second. Notice I put the 3 to the third in parentheses as well as the 3 to the second because 3 to the third should be taken to the power x plus 3. And so I want to make sure I write that properly. And the same thing with 3 to the second needs to be taken to the power x minus 1. Because originally it was written 9 to the x minus 1 and 27 to the x plus 3. Now let's take a look at another property that you should know from your past math classes. That if you ever take an expression a to the b power and you raise it to the power c, a quick way to do that is simply to rewrite it as a to the b times c. You multiply the two powers b and c. That's what we're going to do in this problem. We have 3 to the third raised to the power x plus 3. So to do that, we're simply going to do 3 times x plus 3. And on the right-hand side, in similar fashion, we'll do 2 times x minus 1. Now it looks a lot like example 1 after we did one step on that problem. Now we can simply drop the base 3 and write the equation that shows the exponents have to be equal. Now we'll solve the equation just like we know how, using simple distributive property, adding things and subtracting things from both sides, until we get the x alone. And we get an answer of negative 11. We could definitely plug this in and check our solution to see if we got the right answer. Here's strategy 2. In this strategy, we're going to use logs to solve. So look at our example. It says 4 to the x equals 15. There's no way I can think of to write 15 as 4 to some power. And 4, I could rewrite it as 2 to the second power, but again, 15 cannot be written as 2 to some power. So using the same base will not work. So what we're going to do is use a property of logs that we can use to allow us to drop the exponent. So 4 to the x equals 15. What we're going to do is do a legal move of taking the logarithm of both sides. It's kind of like multiplying both sides by 2 or squaring both sides. It's a legal operation because you're doing it to both sides and it doesn't change the equality of the equation. So we're taking the log of both sides. The reason this is so nice is because now I can use the power rule. The power rule drops the x out in front on the left-hand side so that the x is no longer inside an exponent. That is why we use log, and we use the log on both sides of the equation. So now, be careful, we're using log base 10, So I actually could use my calculator and figure out what log of 4 is and what log of 15 is, but I want to find the exact answer. So to solve for x, I simply divide both sides by log of 4, because the left side said x times log of 4. My answer is log of 15 divided by log of 4, which is approximately 1.92 according to my calculator. This should make sense because 4 to the 1.92 is about 15. We know 4 squared is 16, so it's definitely close to 2 is what the exponent should be. So definitely check your answers and see if you get about the right answer. Of course, we're rounding when we change things to 1.92. Now let's take a look at another example. This one is similar in that the x is in the exponent, and I can't use common bases because I have e to a power, and e is an irrational number, so I definitely won't be able to use common bases. So we're going to use logs. But before we can use logs, one key thing is you got to get the exponential piece alone. So what we're going to do is do some simple math, like add 3 to both sides. And then we're going to divide both sides by 40. So we're getting rid of as much as we can using simple equation solving skills. But now we've come to the point where we have e to the power 0.6x equals 6. To finish this now, we're going to hit it with a log. That's what my high school math teacher always used to say, hit it with a log. We're going to hit it with the natural log because we're dealing with e. And we'll see why in just a minute. So we're going to hit it with the natural log on both sides and use the power rule. So the power drops down in front, and on the left-hand side we have 0.6x times the natural log of e because of the power rule, and on the right we just have natural log of 6. Remember, natural log of 6 is just a number that says e to what power equals 6, and your calculator has that value stored. And the left-hand side, again, we have 0.6x times the natural log of e, which again, natural log of e is just a number. Natural log of e, in fact, is just 1, because e to the first power is e. That is why we use the natural log, because that can eliminate right away and pretty much just cancel out. Now we'll use some simple equation solving skills and divide both sides by 0.6 to get our final answer, which is natural log of 6 divided by 0.6. Again, using my calculator, that gives me about an answer of 2.99. You'll definitely want to be leaving the answers in exact form and checking the decimal form, which allows you to see if your answer is correct or not. Let's take a look at one more example with this one, because this one is a little bit more complex, and you'll see one similar to this in your checkpoint. So again, I have 5 and 4 on my bases. It's not going to be easy to make common bases. I always check for that because that's usually easier. So I'm going to have to hit both sides with a log. Now I'm choosing natural log. What's really important here is it doesn't matter. You can use log or ln log, natural log or regular log. It will not make a difference. Here's why you'll see me and the book using natural log. It's purely because it's less to write. I'm not even kidding. LOG is more ink and more work than writing LN. So you will see the book write things in natural log, and you'll see me write things in the natural log. Natural log also has quite a few more applications. You'll see E used a lot more often, so it's just more common to use the natural log. But again, it will not matter. You'll get the same exact answer when you plug it into your calculator at the end. So I'm using the natural log. I'm going to use the power rule, drop the power down in front. So it's x minus 2 times the natural log of 5 and 2x plus 3 times natural log of 4. Now I'm simply going to use the distributive property. Now this gets a little bit messy, so stick with me here. Remember, natural log is a number. Natural log of 5 is a number. So the first part says natural log of 5 times x minus 2 times natural log of 5 equals 2 natural log of 4 times x plus 3 natural log of 4. So I simply distributed each of the natural logs to all the pieces in the parentheses. The next goal here is to isolate the x, and usually that means to get all the x's to one side and all the numbers to the other. Don't forget that those are just a bunch of numbers there when it says natural log of 4 and natural log of 5. So my first step is to subtract 2 natural logs of 4x from both sides. I'm just simply lining up both like terms. I'm also going to add 2 natural log of 5s to both sides at the same time. Purely, I'm just solving equations at this point. So it cancels off 2 pieces, and gets all the x's to one side and all the numbers to the other side. I'm keeping it in exact form because that's going to be essential to solving equations where we need to find the most exact value that we can. So I've isolated the x, gotten the x to one side, and all the numbers to the other side. Now I'm going to use a simple factoring. Just remember, don't remember, that's just a number. The next thing I'm going to do is factor the left-hand side. I'm factoring out the x. I'm basically undistributing, if you'd rather me say it that way. And the right-hand side I'm leaving the same. The reason I'm doing this is because I want to get x alone, right? So I want to know how many x's are there. Natural log of 5 minus natural log of 4, minus 2 natural log of 4 is just a number. So my last step is to divide both sides by that number because I want to get what 1x equals. And so 1x equals this large expression that you see in the yellow box. That is what x equals. It's an exact answer. I could plug it into my calculator to get a decimal, but you're going to be leaving things in exact form. This is good practice. You're going to be doing calculus soon, and calculus requires a lot of manipulations of symbols and expressions. And so we just manipulated this quite a bit without changing anything to a decimal. So hopefully you wrote this example down. If not, go back and jot it down. Add some questions to it if you got lost anywhere in there. Let's take a look at the final strategy that you'll see in this video before you get to your checkpoints. This one requires factoring and using the zero product property. So we've been doing a lot of factoring this year, so you should be getting pretty good at it. So our first example here is e to the 2x minus 4e to the x plus 3 equals 0. Now here's a couple of reasons why we're going to use the zero product property in factoring. E to the 2x is a different power than e to the x, so I'm never going to be able to get them together or alone. So we're going to factor. Another reason why we're factoring is what we need to realize is that e to the 2x equals e to the x squared. And so this is kind of like a quadratic. We have a squared term, we have a non-squared term, e to the x, and we're going to factor. And you'll see how this works in just a moment. So again, we put our highest power in the one corner, our constant in the opposite corner, and set up our diamond problem. In our diamond problem, we get 3e to the 2x because we multiply across the diagonals. And then we get the minus 4e to the x because of the term we have not used, and that gets split evenly. Now we simply figure out what multiplies to 3e to the 2x and adds to negative 4e to the 2x. And these are the two terms that do that. Put them back in your generic rectangle, and then we'll fill in the outside. Last but not least, we'll replace our expression with what it's equal to. So our dimensions, our outside of our box, is equal to what we originally had in the problem. And of course, that's still equal to 0. Now we'll use the zero product property. Since these two things times each other equals 0, one of them has to be 0. So we have two equations, and we'll get two solutions for this problem. E to the x minus 1 equals 0, or e to the x minus 3 equals 0. Solving the left-hand side by simply adding 1 to both sides, and then thinking about, okay, e to what power equals 1? Well, e to the 0 power, so x has to be 0. On the right-hand side, it's going to be a little bit more complicated. We're going to have to hit it with a log, because we get 3, but we don't know e to what power equals 3. So we'll take the natural log of both sides. Natural log, because it's e, we have to use natural log. It makes more sense. And then, of course, power rule to drop the x in front. And the reason we use natural log is because natural log of e is just 1. And so my answer, I got x alone on the left, and the right-hand side was natural log of 3. So these are the two solutions, 0 and natural log of 3. Plug those in. Make sure you understand that they actually give you 0 when you calculate that out in the original equation. Last but not least, here's your checkpoints for this video. Two problems, one's multiple choice, and one is free response. When you explain your multiple choice question, try to explain which strategy you used. Of course, you can't show all of your work in that Google form, but at least explain what strategy you used and or if you had any questions or felt like you got stuck anywhere. Free response question, again, explaining what strategy you used will be helpful to me to understand if you know the best strategy to use. But you should be getting exact answers for both of these questions. So bring those questions into class. Thanks for watching the video, and make sure to ask lots of questions when you arrive in class tomorrow.